My name is Calderón-Macías. My work seeks to understand wave propagation phenomena for imaging the subsurface, including deriving Earth properties.
Hello, my name is Andrew Geary, and welcome to Seismic Sound Off In-Depth Conversations in Applied Geophysics. In this episode, I talk with Carlos Calderón-Macías, the SEG 2022 Latin America Honorary Lecturer. Carlos holistically explores the near-surface scattering problem. He highlights ways to understand the problem better and why using the noise as signal approach should be further developed. He also explores the differences in the scattered waves for land, ocean bottom, and near-surface data. Carlos shares what inspired this lecture, the three groups perfect for this talk, and the questions he hopes attendees will ask themselves. Not only does this conversation highlight the near-surface scattering problem, but it showcases general approaches for solving any geophysical problem. Visit seg.org/podcast to register for his lecture. This episode is sponsored by Geophysical Insights. Change your tools, change your world. Machine learning technology is accelerating interpretation workflows and yielding new insights in seismic and well data. Check out the guided workflows on the Paradise AI workbench, including stratigraphic analysis, automatic fault detection, attribute generation and selection, and seismic facies classification, to name a few. Paradise is available on premises or in the cloud. Visit geoinsights.com/products to get better tools. And now my conversation with Carlos Calderón-Macías. Well, we are speaking to you today, Carlos, about your upcoming honorary lecture for SEG, and it's entitled Near Surface Scattering and Seismic Data from Signal to Noise and Noise to Signal. The phrase signal to noise will be common for any geophysicist or mathematician for that matter. But what do you mean by noise to signal?
Okay, yeah, it's really a couple of things. So one is near surface scattering is one of many problems that come when analyzing seismic signals. And we often say that noise for somebody is signal for somebody else. So in a general sense, it's somewhat arbitrary what we call noise and what we call signal. I think it depends on the application. And a great example of that, as we geophysicists learn seismology, we learn about surface waves and Rayleigh waves, type of wave that happens when you have an interface between two very different materials, like say air and a solid or water and a solid. So we know them as a surface wave or interface waves. But when you are in exploration, there is this term that people know that is called ground roll. And it's basically a noise, something that we treat as noise, but again, we learn it as a surface wave. So we use a more scientific term. But in engineering, yeah, I mean, you basically see how that is treated as noise and not really as a signal. And there is another example in my talk. There is something that we call shear leakage that we see in ocean bottom receivers. And the shear leakage is a manifestation of near surface scattering. It's just, again, because when people encounter these things, you put it a name that even tells you that, hey, this is noise. This is really not signal. In a more general sense, I'm kind of interested in a very nice principle in science that is called complementarity, which means looking at a problem from different ways. It just helps you to understand better the problem. So switching these words, noise and signal, I think that has that aspect. You try to understand the physics of the noise, and I think we will be in a better place to tackle that problem.
That sounds like a very helpful principle in general there to think about. What is, you kind of mentioned it there at the top, what is the near surface scattering problem?
Yeah, so this happens when seismic waves generated by a source, it interacts with a very heterogeneous media. And that's often the case for the near surface. So the near surface has properties that change kind of rapidly in space. And so things such as topography changing, existence of shallow cavities, sinkholes, shallow channels, and even human-made construction, right, that are kind of in the near surface, what we call near surface, which is really the first 100 meters, say, below the surface. It may be also a smaller scale features, such as the fact that soil properties under extreme weather conditions become quite heterogeneous just due to the weathering. So interaction of these irregularities with the boundary that I was talking about, in this case, air and a solid or water and the sea bottom, that have very different elastic properties, serve some kind of amplification. So when you are near a boundary, what you get are waves that travel in the boundary. So what happens in the near surface scattering problem is that as the waves that are ignited by a source interact with the near surface, and then start traveling in the interface, and because we place our sensors on top of these boundaries, then what we get is very strong signal that often we want to remove.
What's the most difficult task facing geoscientists trying to find a coherent signal when they are processing land and ocean bottom seismic data?
Right. So as I was saying, the main thing is undoing the effect of the near surface geology. So this is and one of the reasons why for me this is a very interesting problem is in when processing seismic data, the free surface or this interface introduces something that we get to describe as noise very often, and probably the best example is multiples. If you have heard the word, so these are multiple bounces from the energy that we inject. It comes up, it hits some kind of a target or geologic objective, right? And then this signal comes up, and then we capture with the receivers. It's just that the free surface sends the signal back again to the subsurface, and so it bounces many times. And so traditionally we treat that as noise. We could use that information also to unravel the subsurface. There is a similar problem that we describe as the ghost effect. That's again, the source interacts with the near with the free surface, and then it produces a secondary source, and it's problematic because every event that we record has this thing that we call ghost event. Right, again, you see that kind of the terminology that it uses to think about noise. And then the scattering problem is similar, because all the data that we record at the surface will go through the near surface, right? So it all is going to be, if we see it as noise, it will be contaminated.
So, Carlos, what are the differences in this scattered waves for land, ocean bottom, and near surface data?
Right. So fundamentally, this is a very similar problem from the wave propagation perspective. So one very important aspect of understanding the near surface scattering problem is that this is an elastic problem. In an elastic propagation, we have compressional waves and shear waves, and the scattering from the near surface really has both types of waves. So both in land and ocean bottom, that representation of the Earth is necessary to understand the near surface scattering problem. Now, at a practical level, there are some differences. In land, the source interacts with the near surface really very quickly, or right at the time that we ignite a source, the wave is propagating at the near surface, and then it goes through the near surface, and then we get our reflection from deeper in the subsurface, and then it comes back and it interacts again with the near surface. In the marine case, it's different. So the source is in a homogeneous layer, which is the water, right? So it doesn't interact with the near surface until it penetrates the water bottom. And then when the signal again comes up, it interacts with the near surface. Because of that, we tend to think that the marine case it might be a bit simpler. In ocean bottom data, I mentioned the term shear leakage. And so what happens in this case is when the signal comes from a reflection deep in the subsurface, and then it interacts with the near surface close to the water bottom as the signal is coming up, because of the interface between water and solid, there is an interface wave that is generated due to the singularities or the changes in conditions of the water bottom. So this is a wave that travels horizontally, and shear waves polarize, they generate motion perpendicular to the direction of propagation. So if the wave is traveling at the interface, which is mostly horizontal for the water bottom, then the energy is polarized in the perpendicular, which is the vertical direction. So when we look at our data, we look at a vertical geophone, it's contaminated by this thing that we call shear leakage, which again is really a manifestation of what's happening close in the water bottom that we normally don't get in environments where the water bottom is not as irregular. Now, in water, we also capture pressure, and the neat thing about pressure is that it doesn't measure shear. So different to land, in marine data, we have this extra component, which is a hydrophone. And so that gives us a way to separate noise from signal, because in one case, we measure the shear signal in the vertical phone, but in the hydrophone, we only measure the pressure. So we use that fact to remove a lot of the noise that we have, the near surface scattering noise that contaminates our recordings. Again, in land, we don't have that feature, so we cannot play that game. So we have to really look at other ways to remove the near surface scattering.
You say in the literature that there have been two general analysis of this near surface scattering problem in terms of its understanding and application, with a little explicit overlap between the two of them. What are these two general analyses? And I guess the next logical question from that is, have you found that there is actually an overlap in this problem?
Right. So to describe it in a way, so when we are trying to get rid of the noise, we usually, what we do is we look at characteristics of that the noise may have versus the signal. Things such as frequency, coherency, the speed at which this noise may travel. If we can somehow discriminate from higher velocities that usually we associate with reflections, then we have a way to discriminate them. So basically, the more typical approach that we follow to remove the near surface scattering problem is to look at the statistics of the data that we are capturing, right? And that, again, those differences, then we point to some kind of scheme that we use those statistics to discriminate the noise and the signal. So that's kind of I call it, say, the data view. The second view is a model-based view where you try to explain the noise as if it were signal, meaning somehow you have a way to model it, right, to reproduce the noise, and then subtract it from the data. It's a very interesting question. Say, okay, what's the overlap between these two? I mean, at a bigger, in my talk, something that I focus is, treating it as the second view. If anything else, it provides for a way to understand the problem. So trying to reproduce the physics of the noise is one way to come up with an approach to use that energy for something that may benefit some other application, and also to remove it if it's really noise that again we need to remove from our signal. The overlap basically there isn't a whole lot. I think in most cases we run to the first view where we remove the noise based on statistics, versus the more complex way where you need to think about how to model this noise.
What viable approaches have you found in addressing this noise attenuation problem?
So I think the statistical approach, and we have a really, really good toolbox for tackling the problem. This is methods and science that were developed quite a bit ago, and also there is the multi-channel schemes where you use, again, the fact that we have a lot of data and some by the kind of acquisition that we do, where we have a lot of sources, a lot of receivers. And so filtering approaches such as bandpassing the data and deep filters, as well as approaches that separate at different scales, in both in time and space. The data have been great ways to tackle this problem. There is an issue because, of course, we don't want to, when we remove noise, we don't want to damage the signal, but also we don't want to change the amplitude of the signal. And that's when it becomes more problematic because we use the data to create an image of the surface, but we also use it to derive properties. So that means that we need high fidelity of our signal. And so when we apply these techniques, it's often that we are damaging a bit of that information. And that's where, the details are quite important. In the model view, there are some simplifications that we do when we apply that view. It means that we need a representation of the near surface on how to model it, and then adaptively subtract it from the field data. I would say that is a commonality to use a cascaded of approaches, not only one, to be able to remove most of the noise. So we could combine, in fact, the two approaches, the statistical one and the model view one, for us to get a better result. And one of the main points of my lecture consists in talking about a multi-component. So when we acquire data in land, we usually record 3 components, 1 vertical, 2 horizontals. In marine data, when we have ocean bottom receivers, we have 1 more component, which is pressure. Using these extra components, that basically means recognizing when the data comes polarized in one direction or another, is also a way to discriminate the noise from the signal.
Why do you think using noise as signal has fewer widespread applications and has been maybe discussed a little less in the literature?
Yeah, so this second view is more holistic in a way, because what we are saying is that our subsurface model, if we can predict somehow the signal and the noise and treat it all together, right, then we would be successful, right? I mean, of course, that requires a model, and deriving a model is not an easy thing. So we call it an inversion process, where we are deriving the properties at certain scale that is enough to mimic either the signal or the noise, and then subtract one from the other. So that's a very expensive procedure, right? I mean, trying to solve the full problem versus the way we treat it, where we say, well, let's first denoise the data, right? Before we start using the signal. This other way of doing it historically has been more efficient computationally, and also less complex. There are less parameters to derive, right? And so that has made it simpler. So in a nutshell, the physics of treating the full signal and noise problem as a one single problem, it's a much more complex problem.
What about your work and study inspired you to develop this particular lecture?
I started working with these kind of waves, what I call surface waves or interface waves, back in my bachelor's degree in Mexico. And then, interestingly, I came up to the same problem at different stages in my career. First, working on land data, and then later with node data. And so, when I was invited by SEG to give this lecture, I think combining these experiences for the time that I was a student to still the fact that I'm still wrestling with this problem, as many people are, then it was a great opportunity to go back to this problem. It's not a new problem. It's been here with us for since I started studying, and even back then. So it's really not a new thing. What is really interesting is that it is still there, and there are still things to do to be able to understand it and tackle it in a better way.
Yeah, it's kind of exciting when you have a challenging problem like this that you can just really, really look at and work at. Who is the perfect audience for this talk?
So I think there are three overlapping audiences probably that could benefit from listening to the lecture. So one is just there is a good amount of colleagues that work in the near surface scattering problem, either because they want to, again, unravel the data and discover the reflection signal, or people that are interested in near surface geophysics. So those ones would be people that I hope, they can join and provide good discussions following the lecture. So that's one I would call it the expert group. The second one is just noise in signals. That's a very general topic, and many people work on this. And this is not really my talk. That it really goes to details on methods to remove noise. But I think that's another group that I'm sure they can ask really great questions and also provide feedback. And the third one is, like I was saying, this is still an unfinished business, so there are still a lot of work to do. So I think it's a great place for students also and people that want to move to within geophysics to a different problem.
Yeah, I think what you said at the top is just kind of that complementary approach of flipping signal to noise to signal, just kind of those kinds of thought models are really helpful, especially for students as they're developing their career and kind of building off kind of these questions idea. What is a question you do hope attendees might ask themselves after this presentation?
Yeah, so there is, in fact, one that you asked me is a great one. The overlap between these ways in which we can see the problem. There hasn't been a lot of work on that, right? I mean, how can we combine these two ways of looking at the noise? One is where we try to model the noise, and second, also look at the statistics that separates signal from noise. I think that provides a good discussion. And there is a second one, I think that something that I don't discuss much in the talk, but it's a very important one. So the near scattering problem is a combination of how complex is the near surface geology, and also the ways in which we acquire the seismic data, right? And so how we place our sources and our receivers, how many components we placed, the frequency of the source, and so on, also plays a very important role in saying, okay, this is the best kind of acquisition that is going to help us to see through the near surface. That's also a great place of discussion and asking questions. Now, a third one that I also like a lot, that I spend some time in my talk, is how this relates to other problems in signal processing. So is there something that mimics or that is as complex as this problem? And as I was commenting, the free surface generates quite a bit of problems for us. So it's the multiples and the deghosting issue, for instance. And the near surface scattering problem goes hand in hand with those problems, in the sense that by removing the interface, if we had some magic way of doing it, then we would have a data that would be much, say, cleaner or simpler to look at.
Well, the next live presentation of this is October 6th, but the nice thing about these talks is that they are recorded, so you can go back and listen to them if you can't catch the next presentation. And I kind of want to end lastly here with a more general question, in that what principle, teaching, or point of view has helped you succeed in your field?
I mean, I would say, Andrew, that one for me that I value a lot is exactly asking questions. So when we look at seismic data, there is a lot of science behind and theory, and there is a lot of looking at data and having questions. I think go a long way in trying to understand the problem, not having one questions but many. So just the fact that we look at a problem and then we find something that we don't understand, then asking questions really has two parts to it. I mean, one is to slow down, right? To see the problem and say, hey, I really don't understand this. And then how do I describe this lack of, say, knowledge or experience to understand that particular problem? And I think it for me, it has never failed, right? I mean, you are going through a problem, and you sometimes we provide relatively quick solutions or answers, and going back later on and saying, okay, I really need to understand this problem in a better way. I would say nothing beats to writing your questions, or having a good idea of which questions do we have, before we tackle. So keeping that open mind to again slow down and look at your mind, right, and say, okay, this is something that I don't understand. I need to think more about it. So not only we should be sharing information, but also sharing our questions. That's also a great way to improve our questions. And as we improve our questions, I think it means we are gaining an understanding on the problem.
Well, you are living out that idea right now as you're sharing questions to consider, as well as helping people understand this topic a little bit more by presenting it. So I appreciate you highlighting this upcoming talk. We'll provide the links for the information to register for this lecture. And Carlos, thanks for taking SEG up on developing this talk and for providing it to other people.
Thanks a lot for the interview, as well as SEG that has this great idea of choosing these topics and discussing them and bringing them to the larger group of geoscientists.
SEG produces Seismic Sound Off to benefit its members, the scientific community, and inform the public on the value of geophysics. To show your support for this show, please leave a 5-star review on Apple Podcasts and Spotify. Simply go to Seismic Sound Off on Apple Podcasts and Spotify on your phone. It takes less than 5 seconds to leave a 5-star rating and is the #1 action you can take to show your appreciation for this free resource. And follow the podcast while you are on the app to be notified when each new episode releases. Original music created by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Geary at 51 Features. The SEG podcast team is Jennifer Cobb, Kathy Gamble, and Allie McGinnis. Thank you for listening. This is Seismic Sound Off, signaling off.